Let's consider this pulley. We have a string wrapped around the pulley, and we're pulling downward with a constant force of F equals 50 newtons. I'm going to skip right away to making a free body diagram so that I can put that on there. Here's my free body diagram of the pulley. And then at the end, we're going to try and figure out what's the angular velocity after a certain amount of string has unwound. All right. Free body diagram. We have acting on this pulley, that force that is 50 newtons, acting straight down. We have the force of gravity of the weight of the pulley, mg, and then some normal force that might be keeping this pulley from falling down, call that F naught. I think that's good. This has some radius r, and we have, oh, it's a capital R in our problem statement, so we'll use capital R there. And I think we're good. Applying Newton's second law, we can say that our sums of our torques are equal to I alpha. Here, when we sum our torques, we have to choose a point to sum them about. If I sum them about the central point, O, then the weight of the pulley and the normal force acting on there don't have any lever arm, so they don't exert any torque. What that means is that we will get just this force trying to spin us clockwise, strike that, counterclockwise. So we get R cross F, which is RF sine theta, where the angle between them is 90 degrees. So it's just RF equals I alpha. All right, lovely. So now we want to know the string does not slip. What's the angular velocity after a meter of string has unwound? Here, I don't know the amount of time this has happened for, but I do know the amount of string that is unwound, and I can relate that to the amount of spinniness that has happened based on my knowledge of the radius and the amount of string that's unwound. Let's write our work energy principle and see if that gets us anywhere. For this, I'm going to draw before and after. So before, we start from rest. After, we have some non-zero omega b as this is spinning. Now I can say that my kinetic energy initially plus my work as I go from A to B is equal to my final kinetic energy. That's 1/2 I omega A squared plus my work is equal to 1/2 I omega B squared. I know omega A is 0. So I can solve for omega B in terms of the other stuff. Multiply by 2, divide by I, take the square root, and we get omega B is equal to the square root of twice the work divided by my moment of inertia, and then take the square root. That's great if I only had the work. Let's see if we can figure out that work. Let's come over here and try finding this work. We'll say that the work is going to be, with a constant force, will end up being our torque times delta theta, but we don't know delta theta. What we do know is we know that torque from the free body diagram is going to be RF. So I can plug in that RF times delta theta. I can regroup this as R delta theta times F, which turns out to be kind of useful because now we can say that that R delta theta is equal to S, where S is that length that we unwind. And we know that length S, we know we unwind 1 meter's worth of S. I'll plug that in, 1 meter times my 50 newtons worth of force, and that gives me 50 newton meters worth of work, or 50 joules worth of work. I can now plug that in over here. Square root of twice 50 joules, and maybe I'll even get fancy and use red to emphasize that's where we substitute it in. And inertia, I don't think I ever wrote that down, but looking back at the problem statement, our moment of inertia of the pulley, radius of the pulley is 0.1, and moment of inertia of the pulley is 2.5 times 10 to the minus third. 2.5 times 10 to the minus third kilogram meter squared. We plug that in, we make sure the units work, which they end up working, and we get a final angular velocity of 200 radians per second.